Right, Chapter 2-1, we are going to be looking at linear and quadratic functions once again, but we're going to start looking at some of the different characteristics and the different ways to write out these equations, not just looking at their parent functions of the linear equation of y equals x and the quadratic function y equals x squared. So we're going to be seeing some of those transformations taking place here. So a few things that we're going to be looking at today is besides linear and quadratic functions, we're going to be just looking at polynomial functions, which both of those are. And then we want to be able to write out linear functions and also write out quadratic functions. So when we talk about linear and quadratic functions, those are both considered to be polynomial functions. So here a polynomial f of x is a polynomial of degree n with a leading coefficient of a sub n that I have here. If you look at the example that I have, this might look like a bunch of gibberish to you right now, but this is what our book's definition gives us for a polynomial function. Now, if I write out a couple examples, for example, if I have f of x equals 7x to the 9th minus 2x to the 5th plus 3x squared plus 7, that right there is a polynomial. And this polynomial here is of degree n, which in our case here is going to be degree 9. The degree is the largest exponent that is on your polynomial. Leading coefficient of a sub n is the term or the coefficient that's with your variable with the highest exponent, which in our case here would be 7. So we have a degree of 9 with a leading coefficient of 7. Just another example here, we could do g of x is equal to 7x plus 2. This right here, this is our linear equation of y equals mx plus b, and we here would have a degree of 1, and then we would also, in this case here, have a leading coefficient of 7. So on the next one here, I have a few examples of polynomials and some non-polynomial functions. And when we look at the first one here, this is a polynomial. And the reason it is a polynomial is because all of your variables here have a, if they do have an exponent, it is an integer, and it's going to be a positive integer. And so if I look at the function f of x here, with the largest exponent being 3, that would be the degree of our polynomial. And then the leading coefficient is going to be the coefficient that is attached to the variable with the highest exponent, which in our case here is going to be 4. On the next one here, 6x to the power of negative 4 plus 7, this is actually not a polynomial. And it's not a polynomial because you have a negative exponent. So we do not consider that to be a polynomial. Therefore, we cannot talk about the degree or the leading coefficient. H of x, a lot of times people think that this is going to be a polynomial function because what people do is they take, okay, 9x to the 4th plus 16x squared, and they take this to the power of 1/2, and then what people like to do is they like to distribute this, and now they end up taking 9x squared plus 16x, and so they say that this is a polynomial. Now remember that you cannot take and distribute a power to a sum or a difference. You can only do that to when you're multiplying. And so what we end up having here is, with this square root here, we do not have, this is not going to be a polynomial. So we will not have a degree, we will not have a leading coefficient. With k of x, in the way that it's written, a lot of times people are going to say, oh, the degree of this polynomial is 1, leading coefficient is 15. Be very careful about that because sometimes it's not written in standard form. And so in this case, since 4 is your largest exponent, that means the degree of our polynomial is 4. And then your leading term, even though 15 comes first, negative 2 is going to be our leading coefficient. And so there's just some looking at polynomial functions. Now we're going to get into two specific polynomial functions today, which is our linear function and our quadratic function. When you think about a linear function, we've been talking about y equals x as the parent function. Now realize that that line is going to be moving up, down, left, or right. It's going to be slanting upwards, downwards, and all of that is going to be based off of our transformations, whether we're sliding it, whether we are shrinking it or stretching it, whatever may be taking place, or even doing a reflection. So when we think about a linear function, it is a polynomial of the first degree. Most likely the equation you associate with a linear function is y equals mx plus b, where you have the slope of m and you have a y-intercept of b. And we cannot, if we have a slope of 0, then what's happening here is we do not have a function because this would end up creating a vertical line. But so to be a function, then it would have to pass the vertical line test. So we'd want for the slope to be something not equal to 0. And then if we look at it more in depth, we know that f is increasing if the slope is greater than 0. So if we have a line that's going uphill, that means that our slope is positive, and so our graph is increasing. It's going to be decreasing if our slope is less than 0, so we'll be going downhill. And the other part to this is that the initial value of the function, which is f of 0 equals b. That right there is the same thing as your y-intercept. So f of 0 equaling b, that's your y-intercept. It's just telling you that on your graph here at 0, you've got crossing that point b. Now what we'll start looking at in the next couple chapters as we start to look at some of these functions, we're going to be looking at lines of regression. And we're going to be starting to look at linear regression. Now, this is something that you may or may not remember from Algebra 2. But what we're looking at here is taking data and comparing it. So you're looking to see if there is a relationship between the two sets of data. And we're going to be looking to see, does it have a linear correlation or not? And there's a couple different ways that we can classify linear correlations or not. And the first one is if you're taking data and you have a study that's being done and you find that all of your data lines up in a perfect straight line, this is saying that in our case here we have a perfect positive linear correlation. So that means as one increases, the other increases. A good example of something like this would be when you are born. So the number of days that you're born, the more weight that you gain. So that's typical of most babies. Then you can have some points that go slightly off of that straight line. Now they're still pretty close to that line, so we call that a strong positive linear correlation. As those points start to drift away from that line, that's when it starts to become a weak. And the reason it's staying positive is because I can still see a trend going uphill as we look at all these data points. And then you have no linear correlations when you got data points all over the place where I don't know where I can possibly draw this line to explain what's happening here. To show you some negative correlations, so here I have a negative perfect correlation because they're all in a straight line. You got a strong negative correlation when the points are close to it, just not on it. And as they spread away, you have a weak negative correlation, as long as you can still see the trend is going downhill. Now, on the last example here, a lot of times people are going to say, oh, it's perfect straight line, but it's not going in a straight line. It's making more of a shape of a parabola, which we don't want. So this here, even though it looks like everything's making a nice line to it, this here has actually no linear correlation. Now, it might have a quadratic correlation, which means we could use a quadratic equation to represent all that data, but we would not be using y equals mx plus b to represent that data. So what we'll be doing in class is we'll talk about how do you do all that on your calculator. And we will be looking at your calculator and trying to figure out how do you come up with what's called the correlation coefficient. The correlation coefficient, what that does is it just tells you how close all the points are to your line of regression. And this value of the correlation coefficient, which is noted as R, is going to be some value between -1 and +1. And where if your correlation coefficient is greater than 0, there's going to be some sort of a positive linear correlation. So your points are going to trend towards going uphill. If R is less than 0, there's going to be a negative linear correlation. So all of your points are going to trend downhill. So if I looked at this problem here, because this has a positive correlation and is perfect, here I would say that R is equal to +1. As we move on here, now the next one here, I might say that R is 0.92. It's still representing a strong positive linear correlation. As it gets weaker here, I might say, okay, we have R is 0.81, something like that. It starts getting weaker. If I have no correlation, then we're looking at correlation coefficient of 0. Here, if I'm going downhill, this would be correlation coefficient of -1. And as we start to drift away from that, here I would end up with a correlation coefficient of maybe -0.93. Here we keep going away from that, so I'd be looking at -0.79. And here I would end up with a correlation coefficient of 0. And so here, like I said, the absolute value of R, if it is approximately 1, that means that we are at a strong linear correlation. So that's like the 0.9, 0.89 is more so strong. As it gets closer to 0, that's where the weak or no linear correlation is going to take place. Moving on then, hopefully that makes sense with all the linear and it's mostly review. We're going to quickly talk about quadratic functions. And when we think about quadratic functions, you're probably used to seeing the standard form, which is ax squared plus bx plus c. Well, what we're also going to be working with is what's called the vertex form. And the vertex form of a quadratic is helpful because it tells you a bunch of things what's going on. First of all, this value of a tells you if your parabola is going to open up or down. It also tells you about the stretches or shrinks, so what's it going to look like. The h is going to tell you how far your vertex moved to the left or to the right. And k is going to tell you how far your vertex moved up or down. So you have the transformations that are taking place in this vertex form. So, when you started with your quadratic with a vertex at 0, 0, we're shifting that around. So looking at just the characteristics of a quadratic function, this is a polynomial of degree 2, and there's 2 different ways that we can write this out, either in vertex form or standard form. And what you're going to get when you graph this out, as we know, is a parabola. It's going to have a vertex of the points of hk, especially when we're looking at it using the vertex form, and you're going to have a axis of symmetry at x equals h. So that's going to be the line that goes right down the middle. It opens upward if a is greater than 0. It opens downward if a is less than 0. Initial value, which is also referred to as our y-intercept, is always going to be the value of c in the problem, and that's if it's in standard form, and you'd have to solve this out and plug in 0 for x into your vertex form to actually find out what your value is there. And then to find our x-intercepts, we can use our quadratic formula to do that. So going back and forth between these two, what I just want to show you real quick is how do you find the vertex of a quadratic and how do you put it then into vertex form? So here I have a quadratic, which I'm going to change this around a little bit, and I'm going to put it into standard form, which is going to be a -3x squared plus 6x minus 5. Because what this is doing right now is it's telling me what a, b, and c are. And I need those values because to find the axis, the vertex, we need to find 2 things. First thing we need to find is your axis of symmetry. Because when we look at this parabola here, which is going to open down, your axis of symmetry is where that vertex is found. And so to find our axis of symmetry, we're going to use the formula of -b over 2a. So in this case here, I have -6 divided by 2 times -3, which is -6 divided by -6, which gives me 1. So x equals 1 is where my axis of symmetry is going to be. This is telling me that my x-coordinate on my vertex is going to be +1. So I'm shifting my graph from 0, 0, 0 over 1 unit for sure. How I'm then going to find the y values, we're going to plug that 1 in for x. So -3 times 1 squared plus 6 times 1 minus 5. And as I work this out, I end up with -3 plus 6 minus 5. And so that's going to give me a +3 minus 5, so I get -2. This now tells me that my vertex is going to be at 1, -2. Okay, here's my vertex. So we went from having your vertex at 0, 0 to now you're moving it over 1 and down 2. Here, if you're trying to now write this in vertex form, you have H and you have K. Now vertex form is A times the quantity of x minus h squared plus k. So we know that we've got h, which is 1, so we've got x minus 1 squared, and k is -2. All I need to do here is figure out what a is. Well, if I look back up into the problem, we know what a is, and a is -3. And so I'm going to put a -3 in here, and now I have the vertex form of a quadratic. Now I could go through the process of completing a square to do this as well, but this is just a little faster and easier. And really all you need to know is one formula and then how to apply it to find the next point. So you may want to go back and watch that again if it wasn't quite clear, or if you have any specific questions, make sure you write those down, because that's all I have on section 2.1, but I want you to do a problem or try and solve a problem and bring it to class with you tomorrow. What I'd like you to try and do here is, if I give you a graph of a parabola which has a vertex at 2, 3, and the graph goes through the point 2, -2, can you come up with a function, the equation, to go with this parabola? So you've got a vertex of 2, 3, it goes through the point 2, -2, and now you're trying to come up with an equation to go out to match that function. So good luck with that, and I'll see you in class.